In the previous section, we looked at modeling the ideal reactor types, the CSTR, PFR, and batch reactor, using the residence time distribution. And we would now like to generalize those equations and those models so that they start to describe real reactor systems. Here's the first such development in the so-called tanks in series model. So according to this model, we have a series of CSTRs. So each CSTR is being fed by its predecessor. So they are all fed with the same flow rate. You have flow rate Q coming in here, and then that moves on to the stream of the next reactor, and so on. And so the exit from the one reactor is the feed to the next reactor. So shown here are three such reactors, and either these are three actual reactors, so it could well be the case that we have three CSTRs and we have the same stream that's flowing through each of them, or it might be that there exists some other large reactor like shown here with three highly mixed zones, and that our depiction here is an attempt to model this real case. So in any event, if we have a series of reactors, we are going to try to develop the RTD for the entire group. So in contrast with the earlier case where we were looking at the model of the age distribution for a single CSTR, we want to know what's the time spent by the fluid if it could be retained in any of these reactors. So for this entire reactor volume, or maybe to look here, for this entire volume, can we deduce the residence time distribution? An assumption we'll be making is that these are all equal in volume. So V1 equals V2 equals V3, and we'll more generally call that VI. We can, of course, see that there does exist an overall an overall space-time here. So the total space-time is V0 over Q. And if these are equal volumes, then this will be, the space-time here will be 1/3 of the space-time of the total system. So remember, space-time is V over Q. So if Q is staying the same, and remember in series here, the flow rates are all equal. And if we are only partitioning the volume, then V over Q gives us here 1/3 of the total volume. So the individual space-time here is 1/3 the space-time of the total space-time. So let's first model just three CSTRs in series, and of course we'll go on to generalize that later. So if we want to know the RTD for three CSTRs in series, then we can of course say that the age distribution of interest, so the exit age distribution, which we call E3, that we established for a pulse tracer experiment, is going to be the concentration that we measure at the exit from that third reactor divided by the concentration observed over all time at that same point. So it's the same development using the same pulse tracer experiment in our development. And let's now, even though that's what we want, in order to get that, remember the pulse is going to come in here. So for example, in the real reactor case, we can't pulse at some random point in the reactor. So we are going to pulse into the inlet stream here. So the pulse is going to come from here. So if we want to predict the concentration out here, we have to develop the mass balance over each of these reactors in sequence to get C3. So to get C3, we have to write balances on each of these reactors. So let's start with the first one. So if we are pulsing tracer in, and we described this fully last time, if we pulse tracer in, that means we'll have some tracer at some initial time T0, and after T0 we don't have any further tracer coming into the reactor. So when we write that material balance, we write that the rate of change of moles in that first reactor is equal to, and there is no flow in after T0. So we'll set that to 0. And so we can specify that this equation is specifically for T greater than T0. So no flow after T0. And then, of course, it being perfectly mixed, the exit flow rate is QC1. So C1 is the concentration in that reactor. So that's the exit flow rate of tracer from tank 1, and that's the rate of change of tracer in tank 1. Note here that as a CSTR, we quite often apply the steady state assumption here, but in this case, because we have tracer being pulsed in, this is inherently unsteady. In other words, we are introducing tracer instantaneously, and then we don't introduce tracer after that. So if we are modeling the tracer concentration here, obviously tracer concentration is changing with time. So this is not a steady state model. So anyway, this is the material balance that we have on tracer in tank 1. And then if we go ahead and divide both sides by the volume VI, then we can see here this is going to be Q over VI, which is 1 over tau I. So again, that's the space-time specifically in that first reactor. And of course, we could call it tau 1 and tau 2 and tau 3, but just to emphasize that it's all the same space-time, we'll just call it tau I. So this tau 1 is tau I, and so the balance is as simple as this. And then, of course, this is a simple homogeneous ODE, and so we can easily solve this, and we can say the concentration of tracer as a function of time is the initial amount multiplied with e to the minus t over tau I. And by the way, in the previous session and in this session, you'll see I'm interchangeably using t and theta. And that's because, remember, we had said that that according to our age lines, theta, our age, is equal to the current time t minus our birth date t naught. And of course, we are free to define t naught. There isn't anything special about a given instant in time, right? According to nature, at least. So according to nature, each time instant is just progressing one after the other, and nature is not trying to label the time instants. So we go ahead and label time. We go and label time according to the different, sometimes religious interests, and as chemical engineers, we are just going to define t naught to be 0. So whatever it is in terms of whatever time scale you like, we can just go ahead and arbitrarily call the time of interest to us, the time of injection, to be 0. So we define the time of injection to be 0. So we can say t naught equals 0, and hence theta equals t. So you'll often see me using theta and t interchangeably in this RTD section. So anyway, I'm not doing that yet. So here we are working in terms of t. And so C1 of t equals C1 naught e to the minus t over tau I. Okay, so that's the concentration in the first tank as a function of time. So here the concentration is changing. We've pulsed tracer in, it mixes everywhere here, and then it slowly exponentially decays out of this tank. And we described in the previous section in detail how that looks. Now we'd like to write a balance. So we have the concentration here, and we are trying to get to the concentration here. So the next step obviously is to write a balance on the second tank, and we'd like to predict the concentration C2 from the second tank. Now in this case, tracer is continuously being fed to the second tank. So in contrast to the first tank, all the tracer came in one instant t naught, and after t naught we had no tracer coming in anymore. In the second tank, that's not true anymore. In the second tank, because the tracer has distributed itself around the whole space here, so not all the tracer is going to exit in the same instant. So tracer will keep exiting the first tank, and so we will have a continuous stream of tracer entering the second tank. And so when we write our balance, we can't ignore the first term anymore. So we develop the balance on the second tank. We can say the volume of the second tank, again, that could be written as V2, but to emphasize it's the same as all the other tanks, we write VI. So the volume times the concentration, that's the number of moles in the tank. So the rate of change of moles in tank 2 equals the rate of moles of tracer flowing in from tank 1 minus the rate at which moles of tracer are leaving tank 2. So that's just flow in and flow out. And of course, tracer is not reacting, so we don't include reaction terms here. Right, so that's the balance on tank 2. And then, of course, C1, we've just gone and found the time dependence for C1. So we can go ahead and substitute that time dependence for C1 here. Okay, so that's the balance on tank 2. Now, this equation is slightly more difficult to solve, and that's because we now have an explicit function in t here, right? Our independent variable of this equation, we have a function in that variable here, right? In the first case, we didn't have that. There was no explicit time that appeared here in the equation, at least. So in this case, it's an inhomogeneous equation, and so we need to think of a different way of integrating this. And we have available to us the integrating factor method. So if you look at the your calculus notes in the first or second year, or maybe even in high school, you will have seen that for equations of this form, where you have dy dx is equal to some function of x, so there's an explicit function of the variable of the equation, and then times y. So if you have some function times y equals some function of x again. If you have an equation of this form, then you can solve it using the integrating factor method, and it has a solution that looks like this. So your solution equals e to the integral of this factor times the integral of e to the opposite sign integral of the same factor times the alpha of x here. So that's the solution. And if we come back to our equation, first of all, we can divide through by vi here. So vi, so it's q over vi, so it's 1 over tau I in this term, and then 1 over tau I in this term as well. And then we move this thing over to the left-hand side. So we can rewrite this as dc2 dt, and then plus c2 over tau I. So that's this term shifted over to the left, and then this term we just retain down here after dividing by tau I. So that's the form of our equation, and now you see it's written in the same form ready for our integrating factor method. So our y is c2, our x is t, and then so there's the c2, and then our beta is 1 over tau I. So a nice easy function for beta, and then excuse me, and then the function in time is this one here. So our alpha is this whole function right here. Okay, so if we apply this integrating factor solution, so here it's also stated alpha is 1 over tau I, and beta is 1 over tau I, and alpha is this. We note here the integral of beta, right? And beta is a constant with respect to theta. So if you integrate this, you are going to get theta over tau I, and you are going over limits 0 to theta. So so if you apply, maybe I should do an intermediate step here. So we can say this equals 1 over tau I, which is just equal to theta over tau. Well, that's what I've got there. So it's theta over tau I, and we are integrating that between the limits 0 to theta, 0 to theta, naught to theta, right? And so you can see at theta, this is going to be theta over tau I, and at naught, this whole thing is going to be a naught. So this is simply theta over tau I, right? So that's the integral of beta, it's theta over tau I. And so when we apply our solution, it's going to be e to the minus theta over tau I, so that's what we write here. And then in here we write e to the theta over tau I, so integral e to the theta over tau I, and then we write in our function for alpha. So alpha is this whole thing here. So there's alpha. And then if you simplify this, so to evaluate this integral, first let's multiply what's inside here. Number one, you can recognize that this is a constant factor, so we can just group this out. So we take that out of the integration. So we just write that there, and then that factor comes in here. And then left over is this e to the theta over tau I and e to the minus theta over tau I. So if you multiply these two together, you get a 1. So there's 1 there. And so if you integrate this, you are going to get theta. So we just take the theta out there, and then that's our C2 as a function of t or theta. It's a little better to write it as theta. Okay, so there's our C2. And then you can do a similar thing for the third reactor. So you go ahead and write VI dC3 dt equals QC2 minus QC3, and then you'll be able to rewrite it in this form. And in fact, let's stick with that form. And now you have to substitute the function for C2. So C2 over tau I is now this thing over tau I. So you'll have a tau I squared down here times this exponential factor here, right? So this is again the standard form for using the integrating factor method. You can see again our beta is the same, 1 over tau I, but this time our alpha has an extra theta and it has a tau squared in the denominator. The rest is the same, right? The exponential term and so on is the same. So now to integrate this one, to integrate this, it looks like this. We've got the same integral e to the integral beta part here, and then we've got the alpha shown here. And this time again we remove the constant, so this time the only constant is 1 over tau I squared, so we take that out here. Also C1 naught, that's another constant we take out. And then out there we had this e to the minus theta over tau I, so that's there. So left over inside here is this e to the theta over tau I and e to the minus theta over tau I. So again, those can multiply together to give us a 1. And then we still have a theta in here. So this time it's integral of theta in d theta. Theta in theta, I mean. And then if you integrate with respect to theta, it's going to be a half theta squared, right? So that's there, and then our integration limits again naught to theta. So if you evaluate this, of course, at 0, this is going to be 0. So this is simply a half theta squared. So a half theta squared, we take that out here, and then the rest stays the same. So now we have C3. And if we summarize these three concentrations, you can see a certain pattern here. You can see that as we consider later tanks, right? If you so that was tank 1, tank 2, tank 3. If we were interested in tank 4, tank 5, tank 6, up to any number of tanks, you can see here that you've got a theta. So here, if you like, we had a theta to the 0. Here we've got theta to the 1. That's theta to the 2. And so you've got a 2 here, and this is for tank 3. So that implies we have theta to the power n minus 1, right? That's one thing we can see. Then also you've got here 1 over tau and 1 over tau squared. And if you like, you could say here 1 over tau to the 0, so that would be a 1 here. So again, you can write 1 over tau to the n minus 1, right? So that's that part. And then here we had 1 over 1, 1 over 1, 1 over 2. And if you think about the source of that 1 over 2, that came from the integration. And we know that over time, if you go back and look at your binomial theorem and so on, if you do this successively, you are going to get 1 over n minus 1 factorial. So for the nth tank, it's theta to the n minus 1, tau to the n minus 1, and then 1 over n minus 1 factorial. So maybe to see that more clearly, you can do the fourth tank in a series and show that that fits the pattern. More correctly, though, you can do this by induction and show that you get that you get the factorial factor emerging there. You also have the exponential part, but that's the same in each case. So the exponential part is the same there. Okay, so as I say here, that's all interesting, but what we really want is the RTD. We want to know the exit age distribution. And we know we can get it by taking the concentration. And remember, we did all this for a pulse input. So we can get it if we take the concentration and divide it by the area under that concentration profile. So for tank 1, we've already derived this in detail in the previous section, so we are not going to redo it here. We'll just state it as known. E1, so we didn't say E1 before, it was just E of theta, but now because n can vary, we'll say E1 is 1 over tau e to the minus theta over tau, and you might want to go back and just verify you agree with that. And now for E2, let's do E2 first. So E2 means we have to take C2 and divide it by the integral under this curve. So we want so C2 itself is easy. C2, we know the function itself, but let's work out the integral under C2. And if you integrate under C2, let's just extract out the constants here, and let's because as constants, there's no reason to, we know that's going to be a constant of integration. So let's just integrate theta times e to the minus theta over tau I. So that's yeah, we took that out and we want to integrate that, and so if you look at this, you see we've got two functions with respect to theta. So we are trying to integrate with respect to theta, but we've got two functions in theta, and so we can simply integrate this by parts. So the integral, the integration formula for by parts, the integral of f times g is of course equal to f times the integral of g minus the integral of the derivative times the integral of g. So we can just apply this integration by parts to integrate this thing. So that's what we do here. So we said the integral of fg is f times integral of g. So that means we just take f out here and then we integrate g. So the integral here is going to be minus tau I times e to the minus theta over tau I. So minus tau I, so minus there, tau I, e to the minus theta over tau I, and then integrating from 0 to infinity. So let's just park that result for now, and then do the second term. So it's minus integral of f dash g. So f we chose to be theta, so f dashed is going to be 1, and let's just write that in explicitly. And then integral of g here is going to be minus tau I times e to the minus theta over tau I. So minus tau, and then times that minus is going to give us a plus, so it's plus tau, and then e to the minus theta over tau. I should say here tau I, right? Okay, so that's one step. And then in the next step, so the first term we found was theta times this, and our integration limits 0 to infinity. Now, if you look at infinity, you've got e to the minus infinity here. And for the exponential function at minus infinity, this goes to 0. So the first term, the upper limit part of this, is going to give us 0. And then at 0, we've got theta here. So this is 0 times whatever comes here. So this is going to be another 0. In other words, this thing doesn't contribute anything to our eventual integrand. So that's a 0. And then leaving us with the second part. And if we integrate this, again, we are going to have another minus tau I times this. So minus tau I times this is going to give us minus tau I squared, and then e to the minus theta over tau I. So that's our integration here. And we go between the limits 0 to infinity. And then again, at infinity, this is going to be e to the minus infinity, which is 0. So that whole thing vanishes. And then we've got e to the 0, right? The lower limit has a 0 here. So this becomes 1, right? E to the 0 is 1. And then it's the lower limit, so it's minus of that. So it's plus tau I squared. Okay, so do this integration carefully and show that the integral of this thing is tau I squared. So if we go back and substitute all that back in, number one, we just substitute for C2 up here, and down in the denominator, we've got the tau I squared, and we had taken out the constant, which was C10 over tau I. So the tau i's here can cancel, and then you've got a tau I up here as well. The C1 noughts can also cancel. So if you do all that, you'll find E2 looks like this. And if you compare it with E1, E1 was just 1 over tau times e to the minus theta over tau. So e to the minus theta over tau is the same. But now instead of 1 over tau, you've got theta over tau squared here. So it's a little different. And then if you follow these same steps, and I'm not going to do it, but please do it as an exercise. If you follow the same steps, you can show E3 is theta squared. And this is, I think this should be a tau I cubed, right? So it's theta squared over 2 tau I cubed e to the minus theta over tau I. So you can prove this as an exercise. So if you put them all together, it looks like this. And again, we can see a progression here. Number one, the e to the minus theta over tau I is the same in each case. Then in terms of theta, you've got theta to the 0, theta to the 1, theta squared. So we can say here theta to the n minus 1. And then you've got, and this should be a tau I. Here you've got 1 over tau I, 1 over tau I squared, 1 over tau I cubed. So this is tau I to the n. And then you can see that factorial term also starting to emerge here. So that's what we can write for for the nth tank in a series, right? It has this general formula. And you're thinking, well, this is all very interesting. Maybe you just like integrating exponential functions and showing off with integration by parts and so on. I won't dispute that, but what we can start to think about is, how does this look as we vary n? And we'll come back to this comment here. But let's apply different values for n now. So once more, we are taking this formula and we are applying n. So we know we can start at n equals 1, and we can use n equals 2, n equals 3, up to any conceivable number. So here, if we look at n equals 1, right, you can see this curve. It's an exponential decay, much like we expect, right? If we apply n equals 2, then you can see we've got this curve here, n equals 3, and we've got this one here. So that's the green line there, and so you can see a slight shift happening. So number one, for n equals 1, we just had an exponential decay, but for n equals 2, we don't start from some non-zero value. We start from 0 when n equals 2. It rises, and then it starts decaying out. So it starts to look more like an exponential decay for later values of theta. And then for n equals 3, you can see now there's a slight, I don't know if you can see it here, but there's a slight curve upwards. So in contrast to this one, which was just curving like that, here we've got a slight upward curve, then it goes through a turning point, and then it starts to show that exponential decay. And you see, as you consider greater values for n, you get more of that pronounced, you get that upward curve more pronounced, and so it curves upwards, goes through a maximum, and then starts to exponentially decay. And hopefully you can see a certain trend here, which is as n is increasing, this thing is shifting further up towards this point, and we are ending up going up higher and falling back down and coming down to 0. So we started out with an exponential decay here, but as n increases, it's becoming much more like a spike, and all the spikes seem to be centered around the same value here. And what I didn't say was, of course, I had to use some numbers in the code, and the code is here if you want to play around with it. But here I just arbitrarily chose a tau of 20, and you can see here this is becoming centered on 20. And think about now among the reactors we looked at, right? We did meet the plug flow reactor, which had that Dirac delta function. We had a spike, and that spike was centered on the space-time 20. Now here I applied a space-time of 20.
I need your...
And you can see that for the exponential decay, you can't really see any special number for that 20. It's not like on this curve we can see a relationship to that 20. But as you apply larger values for n, you can start to see that the curve becomes centered around that 20. So for large values of n, the tungsten series model looks very much like a PFR. And this is quite significant, right? It means that we now have an adjustable parameter, right? We have an equation here, and we have an adjustable parameter n, which allows us to transition between the CSTR and the PFR. And that's surprising to us because when we first introduced the CSTR and the PFR, we described them as being fundamentally different reactor types. We said the CSTR was perfectly mixed and the PFR was perfectly not mixed, but now we've generalized our CSTR view through this adjustable n. And so if we want perfect mixing, we set n equals 1 and we've got perfect mixing. If we want perfect not mixing, if we want it to be more like plugs, then we just increase n and we make n as large as we like to get sharper and sharper plugs. And then we've got plug flow behavior. And we know that neither of those extrema exist in the real world, right? In the real world, you can never get perfect mixing all the time. You can't get, you would have to put infinite energy into mixing to get perfect mixing. On the other hand, you can never get perfect plug flow. You can't have the fluid, you can't control the molecules so precisely that they stay in one perfect plug all the time. At least not in the normal plug flow reactor. So the extreme cases, this one and the pure Dirac delta pulse, those are not real reactors. A real reactor sits somewhere between those two types. And now we have a number that can be used to mimic the real world case. So if you take your real reactor and you pulse some tracer in and you measure the concentration and then you compare it with these curves and you say, oh, looks like my real reactor is following the red line quite closely. So the red line is 4. So it looks like my real reactor is like a series of 4 CSTRs. So that's the great advantage now. So we started out with a very idealized view of residence time distribution. We only modeled the ideal reactor types. And we very innocently took a kind of simple approach. We said, well, what if we had more of those? But when we did that, we eventually found that we could actually model a real-world reactor, the real-world reactor cases. So that's one great step forward we've made now. We are starting to move closer to real reactor types. Okay, so that's on the basis of starting from the CSTR and moving towards the PFR. Now we could ask, could we do the same in reverse? What if we started with the PFR style of modeling? Could we then move over to the CSTR? And that's what we look at here in the so-called dispersion model. So in this dispersion model, we can imagine that we start out as a plug. So we have some tubular reactor and we've got a stream coming in. And we can imagine that when we just enter into that reactor, that we've introduced a new packet of fluid, and so that it's relatively cohesive, and the molecules haven't really had time to mix as yet, so the molecules might be close to a kind of plug there. But as we progress further into the reactor, we get lateral movement. So the molecules start to diffuse away from that original plug, and they start to mix into other packets of fluid elements. And of course, the more time we have in the reactor, the more that's going to happen. So we call this dispersion. Of course, diffusion is a concept that we are familiar with, so we can talk about molecules diffusing around here. But there are other ways that molecules, there are other reasons for molecules to mix laterally. So number one, there's a shear. So there might be no slip at the wall, well, never mind no slip. It doesn't have to be all the way at no slip. There's friction against the wall, and there's viscosity drag. So there's viscous drag with the rest of the fluid. So for other more hydrodynamically related reasons, there's also a tendency to mix laterally. So this term dispersion, right, is something that we as engineers tend to be kind of relaxed about. We say, oh, diffusion, that's a bit too restrictive. I know there's more than diffusion happening. So let's just make a word that sounds close to it. And so let's just say dispersion. Yes, dispersing. So the molecules are dispersing as we travel through. So dispersion is a kind of generalization of the diffusion concept. So we would like now to develop the mass balance with this concept of dispersion in mind. So number one, we can say that if we consider our tracer at some point in the reactor, then we have molecules that are dispersing away from that plug like this. So number one, it could be due to diffusion. So the molar flow rate of our tracer is number one affected by diffusion or dispersion. So you've got dispersion of your molecules, and then number two, your molecules are also just flowing through the reactor. So just by virtue of the fact that we have flow through this reactor, there is a convection term here. So there's dispersion and convection. The sum of those two is the total molar flow rate of our molecules of tracer. So that's just telling us the molar flow rate at some given point in the reactor. What we can do next is write a balance on some fluid element. So if you take Z as the value down the tube, if we select some position Z and we consider Z to Z plus delta Z, then between those 2 points, there exists a certain total number of moles of tracer there. So the volume of such a space is going to be delta Z times the cross-sectional area, and then we can define the concentration there to be C at Z. So the concentration times the cross-sectional area times delta Z, so this is the volume times the concentration. So that's the number of moles inside the space, delta Z. And then
I need your consent.
The rate of change of that we can write like this. So this is the rate of change of moles of tracer between Z and Z plus delta Z. right? And of course, cross-sectional area, if that's constant as we look down the tube, then we don't have to include that. Well, that's not changing with time, that's the point. And then delta z, we are free to pick our distances delta z, so that's all constant in time. So that's one thing we have, and then we can say the flow rate. So we are doing this at some space here, and then the rate of change of moles in there equals the flow into the space minus the flow out of the space. So we can say the flow of tracer at position z, that's what's coming in, and the flow of tracer going out is at z plus delta z. So flow in and flow out. And then of course this is a tracer, it's inert, it's not reacting, so we don't need to include a reaction term here. And then if you just look at this, you can see a function in z and z plus delta z, and we are going to divide through by delta z and take the limit delta z going to 0. So you can see here minus df dz emerging. So there's your minus df dz. And then we had divided by delta z, leaving us with AC dct dt. So that's there. Right? So that's our basic mole balance, unsteady state mole balance on tracer. Now we've got this this expression available still. So this was simply accounting for at some point, at some axial position, the sum of dispersion, the dispersion flux and the convection flux. So Ft, so on the left-hand side of our mass balance, we need to differentiate Ft. So we can just differentiate the right-hand side here. And you can see this is going to be d2ct dz squared, so we write that there. And then here, the velocity, we take the velocity to be constant with respect to z, and of course cross-sectional area as well. So we'll just have your d dz of ct, so d dz of ct. And all these terms have AC in them. Here we had AC on the right hand side, so AC can cancel everywhere. And then that's the PDE, describing how the concentration of tracer is varying with time and axial position in this tube. Right, so that's our PDE, and then we can solve that PDE to figure out how tracer is varying across the space. We can also find a non-dimensional form of this. So if we introduce these variables, so instead of working with concentration of tracer, if we say Ct over Ct naught, that's the dimensionless form of the concentration. And then similarly, instead of working in terms of z, we can say the position z divided by the length of the tube. That's equal to beta. You can see that's dimensionless. And then if we take the velocity divided by the length, we can see that's going to be the space-time, 1 over the space-time. So the current time or current age divided by the space-time, that's, if you like, the fractional, age down the tube. And then we also have this useful quantity, the so-called Peclet number. So the Peclet number is the ratio of your velocity times the length to the dispersion coefficient. So if you like, this thing tells us the competition between convection and dispersion. So these two terms, your convection term and your dispersion term and your convection term, what's the ratio between these two? So that's typified by your Peclet number here. So if you use these dimensionless groups in here, you can rewrite your PDE in the dimensionless form. And then some boundary conditions are described here. So if you say that just to the left of the reactor, there's a convection flux coming in, and that's equal to just to the right you have dispersion into the tube plus convection into the tube. So based on this boundary condition, you can convert that to dimensionless forms, and you can solve the equation. Or if you use open, that means you acknowledge that there might be dispersion even in the tube to the left. So that's another set of differential equations. and then if you solve it, you get this form. And if you know your normal distribution, you'll recognize this as being a kind of modified normal distribution here, and you can see the Peclet number features in this equation. And if you apply a Peclet number that is large, so if Peclet is a high value, then that means you'll have a high convection rate compared with dispersion. That means your system won't have much time for dispersion to happen, and you'll find that this equation gives you basically a plug flow behavior. So your normal distribution will dominate here, and it will give you a sharp spike. And then on the other hand, if you use very low values of the Peclet number, in other words, your convection is small in comparison with dispersion, then the fluid has much more time to distribute itself axially. In other words, you have axial mixing, so you have good mixing, and then you'll find that this equation gives you closer to an exponential decay. So again, we can start from the original statement, which is more like plug flow behavior. And so if this plug passes through fast enough, then it stays close to, then this whole reactor looks more like a plug flow reactor. But if you give it more time, and then there's more of an opportunity for dispersion to happen, and hence lateral mixing, then it looks more like a CSTR. So in a similar way to the CSTR being generalized so that we can accommodate even plug flow, we can start from plug flow behavior and through a single parameter like the Peclet number, or like n in the case of the CSTR. So in this case, using a Peclet number, we can transition from being plug flow-like to being CSTR-like. Right, so this is the first clue that we can model the non-ideal reactor types through these adjustable parameters. And we'll see more of that in the coming sessions.